In this presentation, I'm going to go over Unit 3, Section 1, Part 2 on ionic bonding. We have four objectives here. The first is a refresher on ions. What is an ion and what different types exist? Number two, we'll talk about determining the charge on an ion. This is pretty simple and should go pretty quickly. Number three, we'll talk about how to write ionic formulas, determining the amounts of each ion we have in a certain chemical. And finally, we'll end with number four, the naming of ionic compounds. There's a couple different rules we have to juggle there. So first, let's start with a refresher on what ions are. Ions are formed whenever an atom changes how many valence electrons it has. If an atom loses valence electrons, it becomes positive because it's losing those negative electrons. And if an atom gains valence electrons, it becomes negative because it's gaining negative charges. It's gaining those negative electrons. As an example, we can look at this atom of sodium we have on screen. And I'll bring up a number line on the bottom to represent the overall atomic charge. Sodium will lose its one valence electron. It's going to pop the atom's charge up to +1 because sodium lost its one valence electron. Its overall charge went up to 1. Loses an electron, becomes a +1 charge. If we look at a different example here, we have an atom such as fluorine on screen. Notice that it has one spot open on its valence shell. If it gains one electron, the overall charge will go down by 1. So gaining one electron gives that fluorine a -1 charge. It gained a negative electron, so overall it became more negative. Real quick, let's take a little bit of a deep dive into positive ions. Atoms, when they lose electrons, like we said, they become positively charged. And we call these positively charged ions cations. It looks like it's pronounced cation, but it is cation. And it comes from the word cathode, or the positive end of a battery or a circuit. Lithium, for example, it's going to lose that one valence electron and become +1. Magnesium is going to lose its two valence electrons around the outside and become +2. And aluminum would lose 3 valence electrons to become +3. These are all considered cations. Every single one of these loses electrons and becomes positive, so therefore they are cations. Negative ions, on the other hand, we call these anions when they gain electrons and become negative. We call them anions. This comes from the word anode, or the negative end of a battery or circuit. If we look at examples like fluorine, it has one spot open in its valence shell, so it becomes -1. Oxygen is going to gain 2 electrons to fill that valence shell, it becomes -2. And nitrogen has 3 single electrons, so it's going to gain 3 electrons and become -3 charged. Every single one of these is considered an anion. One quick side note, ionic compounds are not simply two ions put together. They are these huge structures where the ions are combined in a certain ratio. And that image on the right is a good representation of an ionic compound where the charges, the charged particles, alternate throughout this like lattice structure. It's not wrong to think of this as different magnets all kind of attracting one another. These ions, they act kind of like one charge of a magnet. So they're surrounded by the other charged magnets. They have to, it's not like opposites attract is really the rule in this case. So how do we determine those ionic charges? Well, it's pretty simple. Based on the position of an atom in the periodic table, we can tell what the Lewis dot structure will be. We've actually done this in a previous lesson. And if we have these Lewis structures, it's not hard to see what our charges will be. Also, quick note, notice that as the highlighted periodic table shows on screen, it's really only good for our S block and our P block, the left and the right sides of the periodic table. These Lewis structures, it's not as easy to see for the D block, those elements in the center. We'll talk about them in a little bit. So how do we tell the charge when we have that Lewis structure? Well, the element is either going to gain or lose electrons so that it has a full outer shell. Basically, if the element is closer to having no electrons, it'll lose what it has. But if it's closer to having a full shell of 8, it will gain electrons until it's filled. If we notice here on the left-hand side, we have this potassium with one element, with one electron. Because it's closer to 0, it's going to lose that one electron and become charged with a +1. Oxygen, our second example, is closer to a full 8, so it will gain 2 electrons and become charged to a -2. It'll gain 2 electrons right here and here to fill its outer shell. Calcium, it's closer to having 0 than 8. It has these 2 electrons here, but it would need to gain 6 more. So instead of gaining 6 more, it'll lose the 2 it has and become charged with a +2. And finally, fluorine looks like it has 1 spot open here. It's closer to 8, so it'll gain 1 electron and become charged with a -1 charge. So if we continue this throughout the periodic table, we'll see that a pattern starts to emerge. On the periodic table, really, for the first column and the second column, we see that the charge increases from +1 to +2, +3 once we, again, skip that middle block. This column right here doesn't really have a charge. These elements can kind of go in either direction, positive or negative, so they often don't become ions. And then the pattern reverses itself, -3, -2, -1, and the last column is actually no charge because those elements have a full outer shell. So the first exception to our charge rule, as we talked about, the transition metals are a bit odd. That's because most of these elements in the center of the periodic table can have multiple charges. It's really easy just to memorize the important ones, but we will talk about context clues later, actually in this lesson, to figure out what those charges can be. Really, you'll have this set of charges available to you to see what charges are optional for some elements. Notice some of them, like zinc down here in the bottom left, that only has 1 option, but other elements like tin directly above, it could have 2 options. So it really depends on which element you're talking about. But again, we'll go through a context clue you can use later, and you'll always have these charts available to you. The second exception to the rule is that some ions exist as groups of atoms combined together, and we call these polyatomic ions. There's one that is a cation, that's ammonium over here on the left. You can see that the cation here is NH4 with a +1 charge, and there are a whole bunch of these. These you will also have for reference throughout this unit, so no need to memorize, but we will talk about how to use them in just a moment. Know that these polyatomic ions, they still act as single pieces in ionic bondings. So if I have, say, 2 sodium atoms with a +1 charge and one of these SO4 polyatomic ions with a -2, the sodiums act like individual magnets or atoms, and that sulfate, that SO4, it also acts as one piece. So it kind of acts the same way as an atom. So how do we name these ionic compounds? Well, the first rule is very simple, but it only applies to ionic compounds when we have single elements from the left and right sides of the periodic table. And this rule is that the cation comes first and it keeps its element name exactly the same. The anion comes second and it changes its ending to IDE or IDE. NaCl would be sodium and chlorine, changes its name to sodium chloride. Be3P2 changes its name from beryllium phosphorus to beryllium phosphide. And MgBr2 changes its name from magnesium and bromine to magnesium bromide. So that first rule is pretty simple. First element is the cation, keeps its name. Second element is the anion, changes the ending to IDE. Notice the amount of each ion does not matter here. Doesn't matter in example 2 that we have multiple berylliums and multiple phosphoruses. It's still going to be beryllium phosphide. And that's because the charge on these atoms tell us how many of each we have. So question, what would the name for the following 2 ionic compounds be? We have calcium and nitrogen here and beryllium and oxygen here. Go ahead and pause the video to take a guess if you would like. And here are the names for those 2 compounds. Instead of calcium and nitrogen, we have calcium nitride. Instead of beryllium and oxygen, we have beryllium oxide. Now let's talk quickly about determining ionic formulas. The main rule for determining a compound's ionic formula is that the overall charge must be 0. If we have a sodium atom with +1 and an oxygen atom with -2, notice that if we add these up as they are, the total is still -1 down here on the right. So how do we fix this? Well, if we add another sodium atom into our compound, we now have 2 +1s and 1 minus 2, that gets us to an overall charge of 0. So the final formula will be Na2 for the two sodiums, O, and we don't need to write a 1 here. If there's no number, we assume 1, showing there's two sodiums, each worth plus 1, and one oxygen worth minus 2. One quick trick we can do to figure out the formula for this is switch the charges. The charge on the cation becomes the amount of anion, and the charge on the anion becomes the amount of cation. Let's take calcium and phosphorus for a second. If we take the charge on calcium and use it to represent the amount of phosphorus, and the charge on phosphorus and use it to represent the amount of calcium, we get Ca3P2, and this works. This is the correct formula. However, there's an exception to this trick. We need to make sure we have the lowest common factor of each ion. If we take an example like magnesium and oxygen, and we try to switch those charges, we would get Mg2O2. But really, if we take a step back, these were balanced as is. If we have one magnesium and one oxygen, they already have an overall charge of 0. They would add up to 0. So we don't need to do Mg2O2. We just need MgO, one of each ion. You could do the trick as long as you realize afterwards to divide these by the common factor. In this case, divide both of these by 2 to get back to MgO. That's one magnesium and one oxygen. One thing about ionic formulas, this whole thing works with polyatomic ions, but if we have multiple polyatomic ions, we have to use parentheses to kind of keep the formula together. I'll show you what I mean here. Let's take calcium and phosphate, for instance. As is, we have an overall negative charge because the phosphate's worth minus 3, calcium's worth plus 2. Let's add on another calcium and reevaluate. At this point, we have a overall positive charge. 2 plus 2 minus 3 still gives us an overall positive. Let's add on another phosphate. 2 plus 2 minus 3 gives us minus 2. So we're still overall negative. And once we add that last calcium on and we add up the charges, now we have that overall charge of 0. And we could have done the switch trick for this that we mentioned on the previous slide. Our final formula here is going to be Ca3, and we have to keep that PO4 in parentheses to say that there's 2 of the whole PO4. There's 2 of this whole group. We do not need to put parentheses around Ca because it's just one atom. The 3 only applies directly to that Ca. So ionic compounds, when we name these with polyatomic ions, the rule is actually even simpler. The rule is the cation comes first, the anion comes second, and any polyatomic ion keeps their name. So for instance, Na, sodium, and SO4, sulfate, instead of becoming sodium, say, sulfide, it's just sodium sulfate. K, our cation, is potassium, and it stays as potassium. ClO3 is our anion, and it just stays as chlorate. We don't have to change the ending. And in this atom, we have a clue here. Because there are parentheses, we know this is a polyatomic ion, and this is ammonium, so it keeps its name ammonium. The S, though, the anion that comes second, because it's a single element, its chain ending does change to IDE. So instead of sulfur, it becomes sulfide. And our last rule for determining ionic compounds with transition metal ions, the transition metal ions are always going to be cations, so they will come first. But we have to use this rule where we use a Roman numeral in parentheses to show the charge. And we have to do this because these elements can have multiple charges. So we have to show what charge they have. For instance, PbO2 is going to be lead 4 oxide. That's lead Pb, with the 4 afterwards showing its charge. We have Fen, iron 3 nitride, showing that the charge is 3 on the iron. And CuSO4, SO4 being one of our polyatomic anions. This is copper sulfate. However, there's an error here. This shouldn't show copper sulfate. Instead, this should show copper 2 sulfate, showing that the copper has a charge of 2 to balance out the sulfate. Now, the way we figure this out, we'll cover in a short video directly after this. I hope this helped you learn the rules for ionic compounds, what their formulas are, and how to name them.